Hello my dear students, good morning to all of you. In today's session we are going to discuss about very important topic, that is breakdown in electronegative gases. Okay, in the presence of electronegative ions we are going to study about how the breakdown phenomena occurs between the two electrode system. Okay, let us start with the session now. See here, first we should be very much clear with what are electronegative gases. Okay, electronegative process means, before this one, how the gas it is going to be becomes electronegatively. When we say the gas is of a electronegative type, for this purpose a very important process that is going to be called it as electron attachment process, that we have already discussed in the previous session, right? So here electro attachment process means what? Here when we apply the voltage to this two electrode system, the energized particles, which are those electrons, starts moving from this cathode to the anode itself. Is it right? So this electron gets, what will happen when we apply the voltage? The electrons gets attached to this neutral gaseous molecule. Then as a result it will produce the negative ions. How? Is it right? This electron, it is of a negatively charged, right? So this electrons, once it is gets attached to this neutral gaseous molecules or the atoms, means it will produces the negative ions. Getting my point? The gas which is present between the electrode system, example is the gaseous insulating medias, like what? Oxygen is there, nitrogen, sulfur hexafluoride. Is it right? So when this electron gets attached to this neutral gaseous molecules, means the negative ions are going to be produced. So that gas the gas which is responsible for the producing of negative ions, that is going to be called it as what? Electronegative gas. Okay. So I think this is clear to all of you. So electronegative gas means the gases in which electron attachment process plays an active role, that is going to be called it as a electronegative gases. Example is sulfur hexafluoride. So due to this electron attachment process, the gaseous media will get the highest breakdown strength. Okay, so that is nothing but in which free electrons are going to be gets attached to the neutral atoms or the molecules to form the negative ions. I am getting my point? This is clear to all of you now. So now here the electronegative gases, during this attachment process only electronegative gases are going to be produced, right? So the attachment process, there are two types are there, which are those? The first one is direct attachment. So what is that direct attachment? Means here, see this diagram. Suppose this electron, if it is directly gets attached to this neutral gaseous molecule, then it is going to be called it as the direct attachment process, and it will form the negative ion itself. So just direct attachment process, that is going to be represented symbolically like this. So how we have represented here? So this AB it is nothing but it is the nothing but the gaseous molecule. So example, we'll take this A as a sulfur atom and this B as the oxygen atom. Nothing but this is the gaseous atoms, neutral gaseous atoms, what I had considered here. When this electron gets attached to this neutral gaseous molecules, means what it will produce? The atoms, negative ions. Negative ions, that is why I represented as a AB negative here. A means which atom it is? That is the sulfur or the carbon atom, and this B is what it is? B is the oxygen atom. Then when this oxygen or the neutral gaseous atoms attaching with what here? Electrons, charged particles, when attached with this neutral gaseous molecules, means it will produce the negative ions, that is represented by how? AB negative plus h nu it is. H nu is nothing but what it is, where h is the Planck's constant and nu is what? That is the frequency of incident light on the cathode. Is it right? Some amount, packet of energy it is going to be released along with the negative ions. Get my point? So this direct attachment process, it is represented like this. Okay. So second process, what is that one? So that is disassociative attachment process. What is the meaning of this disassociation? Disassociation here means here. So what is that atom what we had represented? A means I had taken it as a sulfur or the carbon atom, and this B is the, so B is nothing but what here? So that is the oxygen atom here. Is it right? So now, so this sulfur and the oxygen atom, when it is attached with the electrons, means the gas molecules split into their constituent atoms. So how we had represented here? So this gaseous atoms are going to be splitted into their constituent atoms. Here we can observe here this AB, it is nothing but sulfur, it is going to be get separated, and this B negative, it is nothing but the, so that is of a oxygen atom. So this is gets splitted. The gaseous atoms are going to be gets splitted up, along with the some electrons are going to be released here. This will forms the negative ions. Getting my point? So what is the basic difference between here is, here a direct attachment means electron it is going to be attached to form the negative ion, but in dissociative attachment process this gaseous molecules it is going to be splits into the constituent atoms here. As a result it will form the electronegative atom and it will give the negative ion itself. Getting my point? This is all about, these are the two types of electron attachment process which are going to be occurs in the gaseous medium. Okay. So now a simple gas, for example what I had considered for this is oxygen gas I had taken here. Others are the sulfur hexafluoride, carbon dioxide and the fluorocarbons. So these are the different insulating gaseous medias which are present between the two electrodes. Okay. So in that, so that only I had explained here. So in that A is the sulfur is there and this B is the oxygen atom. Okay. So now with these kinds of gases, the Townsend's current growth equation, in the previous class we have already derived the equation for the amount of current, the current calculation we have done with the help of an equation, that is I is equal to I naught into the bracket of exponential of alpha into d, it is there. Is it right? So that equation only I had modified by considering what here, by including the both the processes, like which are those, one it is ionization process and one more is the attachment process. Getting my point? Because the electronegative gases are mainly because of the process called as a electron attachment process. Getting my point? So by this electron attachment as well as the ionization, negative ions are going to be formed. So by including these two processes, what I am doing now here, the current growth equation is going to be modified here. So now as we already familiar with the how we are going to be represented, the Townsend's primary ionization coefficient, symbolically how we will represent, that is alpha, right? So now Townsend's primary ionization coefficient, that is represented by alpha, and Townsend's secondary ionization coefficient, how we are going to represent, that is gamma. And now one more symbolical representation, that is eta. So this is going to be called it as what? Attachment coefficient. Keep it in mind. So there are three coefficients what we have considered. The first one is alpha, second one is gamma, and the third is attachment coefficient. How will represent? That is eta. Okay. So under these conditions, so now So by considering these two processes, what we are doing now, the current growth equation modification, what we have done here. So then under these conditions, the current, the amount of the current which is reaching to the anode, another electrode, so that can be written like this. How will write now? I is equal to I naught. Now alpha, it is nothing but the Townsend's primary ionization coefficient, and eta is what we had considered, that is the attachment coefficient. So we'll write like this: alpha divided by alpha minus eta into the bracket of exponential of alpha minus eta into d minus of eta divided by alpha minus eta. So divided by what it is there? 1 minus gamma alpha divided by alpha minus eta into the bracket of the exponential of alpha minus eta into d minus 1. So this is going to be, call it as what? Townsend's current growth equation, by considering which processes? Ionization as well as the attachment process. Okay. So just I had added the attachment coefficient eta in this case, and remaining things are as usual there here. Just I had added the attachment coefficient, that is eta. Okay. Now, so the Townsend's breakdown criteria for attaching the gases. So how this equation can be reduced means by denominator. So this is the numerator and this is denominator. So this denominator term, if it is going to be equating to what? 0 here. When we equate it to 0, what we'll get now? So this is gamma into alpha divided by alpha minus eta exponential of alpha minus eta into d minus 1. So this, when we equate this to 0 means this 1 I can take it to the RHS side. Is it right? So what I had taken here? So this denominator I had equated to 0 here. When we equate it to 0 means this 1 I can take it to the RHS side, right? So this only I had rewritten here. Okay, so this equation shows that, so what it will show, whenever, so there are two conditions are there. The first thing is here, so alpha, if it is greater than this eta, alpha is nothing but the ionizing coefficient and this eta is the attachment coefficient. Suppose this alpha, if it is greater than this attachment coefficient, means in that case the breakdown process in electronegative gases, it is always possible irrespective of the values of what are those? Alpha, eta and the gamma itself. Getting my point? Whenever the primary, Townsend's primary ionization coefficient, if it is greater than the attachment coefficient. So in that case the breakdown process will take place in the electronegative gases, but irrespective of the values of what? These three coefficients. Okay. So next thing here, in another hand, so suppose this eta, attachment coefficient, if it is greater than the Townsend's primary ionization coefficient, means then how will do this one? By increasing the value of the distance between the electrodes as well as considering the gas pressure, as well as by taking the ratio of electric field to the gas pressure, means in that case what will happen means, so this equation I can take this one as a, when this eta, if it is greater than this alpha, means this term it is going to be negligible. Then what is remaining now here? This gamma into alpha divided by alpha minus eta, this will be equal to 1 here, or else we can write the equation for this Townsend's primary ionization coefficient, that is alpha, equal to eta divided by 1 minus gamma here. So this is the equation for what it is, the breakdown process in the presence of electronegative gases. Getting my point? Nothing much here. So the basic thing we need to understand here is how the dielectric breakdown occurs in the presence of which gaseous media, that is of a type electronegative. Getting? So first we need to able to define the what are electronegative gases, then what are the types of this attachment processes. These two are the two processes we have discussed. Then what we have taken here, just Townsend's current growth equation, what we have derived in the previous case. In that itself we have modified by considering what coefficient, that is the attachment coefficient, what we have added here, and modified the current growth equation. Okay, so this is all about what it is, dielectric breakdown in the electronegative gases. Okay, so I hope this is clear to all of you.